Okay. All right. Now, when we talk about factors, in fact, let's start this way. When we talk about rate of reaction, the first thing we talked about, we defined what rate of reaction is. Let's quickly talk about collision theory. Very important before we talk about these factors. Collision theory. Collision theory. All right. Collision theory is the theory of reactions, which says that particles, or let me say, for a reaction to take place, particles must collide. With enough kinetic energy. And when we say we know enough kinetic energy, what it means that the energy must be greater than the activation energy. We talked about activation energy while dealing with MCQ, the multiple choice questions. All right. And so with enough kinetic energy and must collide in the correct orientation. In the correct what? Orientation. Particles must collide with enough kinetic energy and they must collide with the correct what? Orientation. In the correct orientation. This is very, very important. Particles must collide with enough kinetic energy and they must collide in the correct what? Orientation. So if particles collide with enough kinetic energy but not in the correct orientation, we do not have a reaction. These two conditions must be met. Now, we talk about collision frequency. Just going to quickly change this page. Collision frequency. It makes it easy to explain the factors. Collision frequency. The word frequency quickly refers to number. Alright, so this is the number of effective collisions. Number of effective collisions per unit time. Number of effective collisions per unit time. So if I talk about a rate of reaction now, I am going to be standing on this premises saying if collision frequency is high, then the rate of reaction is also going to be what? High. Now, so when we talk about factors that affect the rate of reaction, we are simply saying what are the factors that affect collision frequency. How do I make particles collide faster? How do I make particles collide faster? That's what we are going to ask ourselves. How do I make particles collide faster? Number one, now we talk about the factors. Temperature. And I'm not just going to mention them, I am going to explain in details. How do I use temperature to increase collision theory? Increase in temperature will increase or increases kinetic energy of particles. That's your first point. We're going to try to list 3 points or 4 on everyone. So number one, increase in temperature increases the kinetic energy of particles. All right, particles. So when the kinetic energy of particles increase, what happens? These particles now have enough kinetic energy. Particles collide faster with each other. We are simply saying that collision frequency increases. The collision frequency increases. That's what we mean. collision frequency increases. And once that happens, what's the conclusion? The rate of reaction will increase. Beautiful stuff. Beautiful. So increase in temperature increases the kinetic energy of particles. Collision frequency will then what? Increase. Once that happens, rate of reaction will increase. So if the examiner says, how does temperature affect rate of reaction? This is what you say. Increase in temperature increases the kinetic energy of particles. That's number one. Number two, collision frequency will what? Increase. Therefore, rate of reaction will increase. So we are saying the higher conclusion, the higher the temperature, the faster the rate of reaction. But the mechanism is what we have explained. The faster the rate of reaction. So that's number one. We're looking at 6 of those factors. Number two. Let's go to number two. The higher the temperature, the faster the rate. That's the conclusion. But the how is what we have written here. Good. Number two. Let's look at number two. Concentration. And this you talk about aqueous solution. Alright? So what's the first point? Increase in concentration increases the number of moles per unit. Increases the number of moles per volume. Per unit volume. Alright, remember concentration is N over V. Good. More particles, so you have more particles now. More particles are available for collision. More particles are available for collision. Oh, when that happens, what's the next thing? Collision frequency increases because there are more particles now. They collide more frequently. Collision frequency increases. And if that happens, what do we say? The rate of reaction will also what? Increase. Again, that is the trend. What is the conclusion? The higher the concentration, the faster the rate of reaction. Again, that is our conclusion. That's number two. Number three. Alright, so this is a quick crash course for everyone who's watching. Old Matric or new Matric, you're upgrading, trying to, put everybody into perspective. Pressure. And when you talk about pressure, you only refer to gases. Alright, an increase in pressure. And how do you increase pressure? An increase in pressure, which is a decrease in volume, Boyle's law. Alright, what will that do? Will decrease the distance between particles. Will decrease because the particles are now closer. Will decrease the distance between particles. Alright, we are saying particles are now closer. Particles are closer. So what happens? They tend to collide more. Alright? Because they are closer, they collide and generate more kinetic what? Energy. So I'm going to put here kinetic energy of particles will increase. Therefore, collision frequency increases. So if you notice all along, I keep writing that statement, collision frequency increases. And then, what is the final thing? Rate of reaction will increase. All right, and what be my conclusion? Increase in pressure. No. The higher the pressure, the faster the rate of reaction. Awesome. Number 4. I hope we are connecting. Number 4. Let's look at number 4. So we've looked at number 1. We looked at what? Temperature. Number 2. We looked at concentration. Number 3. We looked at pressure. Number 4. Let's look at the 4th point. Surface area. All right. Surface area talks about the number of particles exposed to a reaction. So, the larger the surface area, let's start from, let's say, a large surface area, because I don't want us to conclude. A large surface area makes more particles available. For collision. All right, that's the first point. Number 2, so if more particles are available for collision, collision frequency will what? Increase. Collision frequency does what? Increases. And when that happens, what do we say? The rate of reaction will increase. So if you notice, there's always that statement before the last one. Rate of reaction will increase. So we are saying that conclusively, the larger the surface area. So when I talk about this, I'm actually referring to solids. The larger the surface area, the faster the rate of reaction. Beautiful stuff. This is beautiful. I'm telling you, this is beautiful. Thanks to SOWETO TV, this is amazing. All right, number 5, catalyst. Number 5, catalyst. Now, what is a catalyst? A catalyst is a chemical substance that affects, and in this case we're looking at a positive catalyst, so we would say that increases the rate of reaction. This is a positive one. All right, without itself taking part in the reaction. Without itself taking part in the reaction. And what does this mean? This means that the chemical composition remains unchanged. The chemical composition of the catalyst, chemical composition remains unchanged. All right, you need to know that statement because an examiner can use that. Now, how will a catalyst do that? A catalyst lowers the activation energy We talked about that when we're doing multiple choice. Lowers the activation what? Energy. Remember what activation energy is? Let me use a different color there. That's a keyword there. What is activation energy? The minimum energy required. The minimum energy required to do what? To start a reaction. All right. So a catalyst does what? Lowers that activation what? Energy. I'm going to draw a graph now. All right. What happens here? Collision frequency will also increase because particles reach the activation energy quicker now. Collision frequency increases, and then okay, no, there's something I'm missing. A catalyst lowers the activation energy. Let's do this by creating an alternative pathway. By creating an alternative pathway. That's also an important point. An alternative pathway for the reaction. And therefore, collision frequency will increase. Collision frequency increases. Collision frequency increases. And when that happens, I'm sure you know the next point. I'm just going to write it here. Rate of reaction does what? Will also increase. Beautiful. Rate of reaction will also increase. Let's draw a quick graph just to explain this further. I'm sure some of you are writing, so I'm just going to wait a little bit. A catalyst is a chemical substance, and I told you we have what? Two types of catalyst, but with our scope, we are going to focus on what we call a positive catalyst. That's why even if you don't write affect, you can write that increases the rate of what? Reaction. Or that speeds up the rate of reaction. And a catalyst will lower the activation energy. Collision frequency will increase, rate of reaction will increase. I'm sure we're done, and I want to just quickly show us the graph that we are talking about. So this is the energy profile, all right, of a reaction. All right, so we talk about energy there. Okay, now this is my reactant and that's my product. Don't forget, we spoke about this under multiple choice. We measure activation energy from the reactants to the activated complex. So this is EA. Okay, so this is a typical reaction here. All right, number of particles here. Now, what happens is this. When we now throw in a catalyst, I'm going to use a different color here. This still remains the same. The heat of the reactants remain the same. All right, it goes up, and what happens? We lower the activation energy. That still goes there. All right, but what happens? This has now been lowered. The value there compared to the value there is lower. This is the activation energy of a lowered activation energy of a catalyst, EA catalyst. It is lower. So that's the alternative pathway that we refer to. Alternative pathway. So that, look, we are saying, for example, if this was 500, for a reaction to take place, you need 500 kilojoules of energy. But here, I have 350. So once the energy builds up to 350, reaction starts taking place. Collision frequency would increase, and then rate of reaction will increase. So this is the energy profile for a catalyst. Energy profile for a catalyst. All right. So you might be given such things. Please understand the lowered one, lowered EA, the yellow one. Let me do that here. Lowered activation what? Energy. Awesome. Now, we go to the sixth point and then talk about Maxwell-Boltzmann distribution. From there, we are going to answer our questions, and then hopefully we'll do some stoichiometry. The last one is number 6, the nature of reactants. All right. Reactants, or we can say elements and compounds, react differently. For example, your group 1 elements are most reactive. Okay, so elements that are more reactive, elements or compounds that are more reactive will have a high collision frequency. Will have a high, let me continue here, will have a high collision frequency. And if that happens, the rate of reaction will also increase. Okay, now let's quickly look at Maxwell-Boltzmann distribution curve. Maxwell-Boltzmann distribution. All right, this is really a crash course. Maxwell-Boltzmann distribution. Number 1, let's look at the one for concentration. Okay, it's a crash course, trying to remind us of the things we've learned during the year. All right, concentration. So we could have, that concentration, C1. Lovely. And here, there's one place that will always be constant here. We talk about activation energy here. Now, if you look at this, this is concentration, C1. The number of particles that will only react will be here. All the particles that are here will not react because they don't have enough kinetic energy. This is number of particles. And that is kinetic energy. So only this section will react because their energies are above the activation energy. However, if we increase concentration, I'm going to draw C2. Guys, maintain the shape. This needs to go up because we have increased our concentration. What do you notice? There are more available. All right, more particles are now available. So C2 is greater than C1. That's your Maxwell-Boltzmann distribution curve for concentration. The higher the concentration, you have more particles available to have kinetic energy above activation. So more collision frequency and the rate of reaction will increase. I hope that makes sense to us. Okay, number 2, still looking at Maxwell-Boltzmann distribution. Number 2, let's look at temperature. We're going to look at 3 of them. Temperature. Again, what do we have? EA. Alright, let's call this T1. So only these particles will react. Now, if I increase temperature, what happens? If I increase temperature, the particles here will gain kinetic energy such that they move towards the side, because here we measure kinetic energy. What will my graph then look like? T2. Maintain the shape. Now, what has happened? The particles under T1 area here have now gained kinetic energy such that their kinetic energy increases. The particles that remain are now smaller. That's why this graph comes down. Remember what this is: number of particles. So the particles gain so this one here have gained more energy and they've moved towards the side so that we have more here. Do you see we have more particles now? And here the amount of particles has decreased. So please take note of this graph. Very, very crucial. If I increase it more, I will then have this T3. So T3 is greater than T2, and both are greater than what? T1. Okay, this mathematically, you know that this inequality is terrible. It's wrong. So let's do this. All right. So you have T1 as the lowest temperature, and followed by T2. T3 is the highest temperature. This is your Maxwell Boltzmann distribution for temperature. All right. So please take note. The more you increase temperature, more particles tend to fall over activation energy, therefore having enough energy above activation energy. Good. Number 3, catalyst. Catalyst. All right. We have our activation energy. Now, what will a catalyst then do? Remember, this is EK. These are the particles that are first available. When we introduce a catalyst, this is what happens. Our activation energy is lowered, which means I am going to now shift. This is the only one where you shift the activation energy. So I'm shifting it backwards because it has now been lowered. It has been lowered. So this is EA of catalyst. So what happens? Look at all the particles that are available for reaction. Once you have more particles available for reaction, automatically rate of reaction will then increase. I hope that makes sense. That's your Maxwell-Boltzmann distribution for a catalyst. Great. Now, conclusively, let's see, how do you measure rate of reaction? How to determine rate of reaction? There are different ways. Number 1, if my product is a gas, for gases, what do? We collect the gas with a syringe. Collect the gas with a syringe. Measure the volume per time. Measure the volume per time. And then do your calculation. All right. If it is a solid, what do? Weigh. Weigh the mass before and after. Okay. Now, when you talk about a substance that forms, we talk about turbidity. A substance that forms a precipitate. All right. Precipitate. And how would you know? You will see that a solid is formed at the end of the reaction. All right. A precipitate. Measure the time. it takes for the precipitate to form. Measure the time it takes for the precipitate to form. For the precipitate, I'm just going to write PPT to form. Awesome. Now, please note, when we talk about the rate of reaction, when reaction stops, I'm going to draw a graph again. When reaction stops, it means that the limiting reagent has been used up. Limiting reagent has been used up. Okay, now there are three phases of a reaction. So we're trying to determine the rate of reaction. There are three phases of a reaction. Okay, and we would then use a graph. I'm trying to, some of us are writing. Okay, however, the PDF is available. Okay, now the three phases of reactions are this. So we are going to measure this against time. All right, and probably concentration here. Good. Now, these are the three phases. Phase 1, phase 2, and the third phase. Here, reaction rate of reaction is fast. Why? The gradient is very steep. I would like to use a different color here to write all of this. Okay, so this is our first phase. Phase 1, rate of reaction is very high. Why? Gradient is very steep. Here, rate of reaction is slower. All right? Why? The gradient is gentle. Gentle, TLE. And from here, it's a flat curve there. Reaction has ended. Reaction has ended. And why do I know that? Because we no longer have anything that is being produced. Okay, now this is actually talking about products. Let me claim this. We'll talk about this when we talk about something formed, a product formed. Product formed. So you could be talking about a gas formed, or you could be talking about a solid formed. All right, so the mass of the solid formed is increasing, or the volume of the gas collected is increasing. Gradient reaction has stopped there. We have zero gradient. All right, and this is T, this is 0 here, T1, T2. It doesn't matter if this continues. Reaction actually ended at that time. Reaction ended at T2. I hope that makes sense. But notice this graph is for products formed. Products formed. All right, this is when we form products, whether we form a solid or we form a gas. What about if I want to use a reactants to do this? What will my graph look like? I could have just cloned that, no, but it's okay. What will my graph look like? So be careful with the graphs. We are about to answer a few questions now. It's the same division that we had. Phase 1, phase 2, and phase 3. The same explanation. But here we are talking about what? Reactants, because they are now being used up. And at this point, reaction has ended. All right, so here we talk about fast, we talk about slow, and we talk about no reaction. Good. Guys, this is it. And then we can now do a bit of stoichiometry based on the question we are going to have. Let's quickly answer our questions. This has been so interesting. Rate of reaction simplified. All right. No. Oh, this is Maxwell Boltzmann. I think there is a question we need to start with. I'm just going to go back quickly. Oh, yep. Let me quickly bring back this page. Remember, we got to the topic and then we summarized the whole topic. So now let's answer our question. Wow, we went quite deep in the summary. Okay, I'm almost there. All right. Good. Let's answer our questions now on rate of reaction. Learners use the reaction of sodium thiosulfate. Once you see sodium thiosulfate, I want to show you something here. With dilute hydrochloric acid, the formula for sodium thiosulfate, you don't need to cram it, please. But this is what I want you to see. Look at my product. My products are sodium chloride, which is aqueous, sulfur dioxide, which is a gas, and that is given up from the system. We form a solid. If we form a solid, it's a precipitate. That's where we talk about turbidity. And we have water, which is a liquid. Very important that you look at the phase system. All right. Now, the first question says, define reaction rate, which we did. All right. 5.1. Let me remind you, it is the change in concentration of products or reactants. But remember, per unit time. There are other definitions that we can use. You can talk about the change in number of moles, change in the mass of either reactants or products per unit time. So the change must be that the products have been used and the reactants have been formed per unit time. All right, we have, look at this next question. The investigation, 5.2. I hope 5.1 was quite easy. Please expect that to be your first question when you get into your exam hall. All right, now the three investigations 1, 2, 3 are carried out. The results obtained in investigation 1 are shown in the graph below. For this investigation, check this. The reaction rate is on the Y, concentration is on the X. This examiner is very clever. For this investigation, write down the dependent variable. Please understand that your independent variable will be plotted on the X index and dependent will be plotted on the Y. Don't forget the word index. Now, my X here is concentration and my Y is rate of reaction. So when the examiner said, for this investigation, write down the dependent variable, they're talking about the Y-axis. And what's your answer? Rate of reaction. So this is examiner using graphs to deceive us. 5.2.2. Conclusion that can be made from the result. What do you notice? Do you notice that as the concentration was increasing, the rate of reaction, do you see that? Check the point. All right, rate of reaction increases based on concentration per mole. So the higher the concentration, the faster the rate of what? Reaction. All right, so we can therefore say, make sure your English is very simple and you use terms. All right, reaction rate increases. Reaction rate increases with increase in concentration. Awesome. Is that okay? Is that awesome? Please don't say directly proportional. If a graph does not start from 0, don't use the word directly. A graph that starts from here, if I start from here, then you can say directly what? Proportional. But if I don't start from the origin, please, you would lose 1 mark. Alright, just the reaction rate will increase with increase in what? Concentration. Alright, not directly proportional, please. If it doesn't start from 0, it's not direct. Okay, awesome. I hope that's fine. 5.3. The Maxwell-Boltzmann distribution curve A and B below represents the number of particles against kinetic energy. I think we've answered this question already. What does the line P represent? What do you think the line P represents? If you were listening to my teaching and summary there, 5.3.1, activation what? Energy. We did all of this. Activation energy. I'm sure right now you wish you were listening if you missed something out in my summary, because everything is now well stated. Which curve A or B was obtained at higher temperature? B. 5.3.3. Explain in terms of collision theory how an increase in temperature will do what? Influence the rate of what? Reaction. We've explained all of that, but I'm going to do that again for you here. It's 4 marks. Expect to write 4 points. What happens? At higher temperature, alright, particles move what? Faster, because they gain kinetic energy. Particles gain kinetic what? Energy and move faster. If you remember, this is basically a repetition of what we did. Now, more particles have enough kinetic energy, have enough kinetic what? Energy above activation what? Energy. Number 3, collision frequency increases. Now, they said how it influences. The final one, your conclusion, rate of reaction will increase. Awesome. So at a higher temperature, particles gain kinetic energy. More particles have enough kinetic energy above activation energy. Collision frequency increases and rate of reaction will increase. Just want to go back and check what we have here on the temperature. All right. Increase in temperature will increase kinetic energy of particles. I want to include this point here. More particles have enough kinetic what? Energy to collide. I want us to include the word more. And number 3, collision frequency would what? Increase, and then rate of reaction. So basically, guys, you see your 4 marks there already listed out for you. Beautiful. This is just beautiful. All right. Now, 5.4. Investigation 3. 5.2 was investigation 1. Let's look at 5.4. Investigation number 3. I hope we're getting there. Make sure you have some food to eat. All right. Make sure you have some food. You don't want to lose any moment here. The potential energy diagrams X, Y below represent, the reaction under 2 conditions. Okay. Under 2 conditions. Let's check. Give a reason why curve Y differs from X. All right. Give a reason why curve Y. This is similar. Guys, I have already answered this for you. Do you want me to show you? This is what the examiner is talking about. Where is it? Where is it? Where is it? That's what the examiner is talking about. Do you see? Reactant products there. This is what the examiner, my God, this summary is just the best summary that you can actually ever think of. It is so detailed. All right, it is completely detailed. Remember, subscribe. When you hit the like button on our YouTube channel, please make sure you subscribe, leave a comment, and tell someone how this summary is so important. So 5.4, give a reason why curve y different from x. Y was obtained using a catalyst. Done. 5.5. There's a bit of stoichiometry. Now, in one of the investigations, okay, this is where I really want. I love this stoichiometry. In one of the investigations, 100 cm cube, let's see what we have. 100 cm cube of a 0.2 moles per dm cube hydrochloric acid. Guys, I always like to write what I have. Check this. My reaction was Na2 S2O3 plus, I think it's 2HCl. Let me just quickly get that equation again. I'm just looking for that. Okay, Na2S2O3 2HCl. Okay, beautiful. Because I think, and that will give us, let me just copy it. I wrote it down somewhere. Okay, let me copy that quickly. Because I'm going to need it. Just get my keyboard. Okay, I delayed. I just need to get that. Beautiful. I want us to do the stoichiometry, and I'm going to use a fresh page. Awesome. So that's the reaction we have. I'm going to move this. Okay, and then we have water. That one can go. Nice. So this is what I have. Na2S2O3 plus 2HCl, just to make it look better. 2NaCl, sulfur dioxide, sulfur plus water. Okay, now sorry for my being a perfectionist to a point. Okay, so we have this reaction. Now, what do we know? It says in one of the investigations, 100 cm cube of a 0.2 mole hydrochloric acid, moles per dm cube hydrochloric acid. Wait, 100 cm cube. Let me quickly write what I have. 100 cm cube. I'll come here and cancel some things out. 0.2 moles per dm cube. I'm just quickly transcribing all the information. All right. React with excess sodium thiosulfate, and the solution is filtered. After filtration of the solution, 0.18 grams of sulfur is obtained. 0.18 grams of sulfur. So I am writing all the things I know under each reactant. Calculate the percentage yield of sulfur. Grade 11. Percentage yield. We're looking for percentage yield of sulfur. Percentage yield of sulfur. Great. Now, the first thing I need to do is I'm going to, okay, please understand it's already balanced. Okay, it is balanced. Now you are going to work with number of moles. Check here. My volume, guys, we don't work with cm cube. We work with dm cube. So I'm going to divide this by 100 or by 1000, and that will give me what? 0.1. Please, we work with dm what? Cube. Moles per dm cube. Moles per dm cube. Now, this is concentration. Do you notice something is missing here? Number of moles is the key. So number of moles is CV. which is what? 0,1 times 0,2. All right, I know this will give me 0,02 what? Moles. Now check this. Mole ratio. HCl, I am dealing with HCl and sulfur. 2 moles, that 2 there, should produce what? 1 mole of that, according to my balance ratio. But how many moles do I have here? 0,02, which would produce number of moles of sulfur. We can then cross multiply. I want to keep my calculation here on this page. Sorry. Okay. So now if I cross multiply, basically it's half, but let's just do it. 2n will be equal to 0,02. So the number of moles of sulfur will be 0,01. Alright, 0,01. So this is the number of moles of sulfur produced. Now, since we're talking about percentage yield, now we can calculate the mass. Number of moles is mass over molar mass. Number of moles is 0,01. What is the mass? I don't know. What is the molar mass? The molar mass of sulfur is 32. Please, you need to check. And when you cross multiply, M is 0,32 grams. This is what we had produced, and this is what we should produce. So the real reaction, now percentage yield, what is the formula? I should have given you the formula. Percentage yield is actual yield, what we really produced, over theoretical yield, what we calculated. Because we're talking about what percentage did we produce from what is expected. Alright, so our actual yield was 0,18. Now, theoretically, we are expected to produce 0,32. Now, that's how you calculate percentage yield, stoichiometry. Okay, and then we do the calculation. 0,18 divided by 0,32, and that multiplied by 100. Missed my dot, and my answer is 56,25%. 6 marks. All right, so percentage yield is actual yield over theoretical yield. Please, here is your key. Work with number of moles. That's your main aim. Number of moles. Alright, so calculate number of moles of given substance. Number 2, use mole ratio. Mole ratio to get number of moles of required substance, and then manipulate your number of moles, manipulate N, whether you are going to look for mass or you are going to look for concentration based on number of moles. That's where it starts from, and then you do your final calculation. It's always based on number of moles. Please don't forget your standard unit. Volume is measured in dm cube. Please, volume, I run and repeat, volume is measured in dm cube. Volume should be in cubic decimeter, and this is cm cube divided by 1000. Please take note of that. All right, that is our rate of reaction done. All right, in case you want to put down a few notes, rate of reaction is now done. I'm sure you are done as well, and you understand. Let me go back again and let's see. So we calculated number of moles based on what we are given. All right, we got the number of moles as 0,02. Then we used our mole ratio. Look at how I represent my own mole ratio. And do you know why I'm using this too? HCl and sulfur. That's what I am given. I am given information on those two. Compare the mole ratio, got the number of moles, calculated the mass, and then substituted in my formula, and I am done. Beautiful stuff. I think we should then move to the next question, which is chemical equilibrium. I'm sure a lot of you have been waiting for this hour. Chemical equilibrium, you're really craving for this time. All right, here is your time. Let's deal with chemical equilibrium. Awesome. Chemical equilibrium. Now, let's get a fresh page. What is it that I should know when I talk about chemical what? Equilibrium. Again, let's do a crash course on chemical equilibrium.